So, easy example, circulation. And now we have a couple of examples in each category, geometrically and physics point of view. But let us see how dramatically different those are if you try to bring one to the other. So let me take this easy example of translation. And see how that can be represented from physics point of view or algebraically. Well, translation, for simplicity, let's take translation in a plane from when each point moves to the right by the amount of 2. So a way to go from geometry to physics would be through algebra. So let's figure out the formula for this translation. So what would be the value of the function at any point xy? Well, if I introduce coordinate system, this probably simplest way so that the x-axis is parallel to the direction of translation, well then my translation keeps y value the same and increases x value by the amount of 2. So I get x plus 2 and y stays the same. So that's the algebraic formula for the function. Very simple formula, and we notice that this function is linear. Right? Don't we see immediately that this function is linear? Well, each variable is used here in a polynomial fashion of degree 1. So algebraically we clearly see it is linear. Do we see that this translation is linear? Well, probably you can agree that this translation is linear. Everything is moving linearly. Now, what would that be from physics point of view? Well, if we look at this function and we assign to each point xy a vector with coordinates x plus 2, comma y. Alright, let's play with that. So what is going to be the vector assigned to the point, let's say 1, 1. If x equals 1, y equals 1, the vector is going to be 3, 1. 3 horizontally, 1 vertically, so this kind of vector. Alright, what about the point 0, 1? If x equals 0, y equals 1, we have 2, 1 as a resulting vector, 2 horizontally, 1 vertically. And you notice, well, this is a different vector. That vector 3, 1 is different from this vector 2, 1. So these 2 points move with different velocities. Let's move a little. -1, 1. That results in a vector 2 minus 1, 1, 1. So that is yet another different vector, 1, 1. And if I move one step further to the point -2, 0, the resulting vector will be 0. Oops, sorry, that's point -2, 1. The resulting vector is 0, 1. So it is vertical. So you see that the same formula interpreted in physics when we assign a vector to each point gives us different vectors for different points. And can we now understand what kind of flow that is? If this point moves this way, that fast, this point moves that way, that fast, and so on, well, we definitely have to plot more points, more vectors. What about this point? It is 1, 0. Well, it moves with velocity 3, 0. So it moves that fast to the right along the x-axis. What about 0, 0? It moves to 0. It moves also right, but slower. The point minus 1, 0 moves with velocity 1, 0, moves to the right, but slower. And the point minus 2, 0 has velocity 0. Stays the same. This point doesn't even move in this process, in this flow. And let's play a little more. What about this point 0, minus 1? If you substitute 0 minus 1, you get 2 minus 1. So 2 to the right, 1 down. Vector is like this. And the point minus 1 minus 1 results in a vector 1 minus 1. 1 minus 1 is a shorter vector going down. And that point minus 2 minus 1 results in a vector 0 minus 1 that looks down. So we may suspect that what happens here is probably every single point is going to move away from that central point. And if you continue plotting those vectors, this is exactly what you will see. So the whole flow, as described by those velocities, it seems like explosion. So this is explosion from that center. And now you see how different this picture is from that one. This is very simple. Everything moves the same way. This is not that simple. Everything moves away from the center, and the further you go from the center, the faster the particles move. So, all right. And that, by the way, was not even one of those simple examples we figured out at the beginning.